Basic calculation, optimization 2. Now we're going to deal with formally with more than one variable. Just a reminder, find the expression for area. If you're finding a maximum area, you find the expression for area. It may only have one variable. That's very important. We're going to go more into that now. The minimum or maximum will occur when the derivative for that area, dA by dx or dA by dr or dA by dl, whatever, is equal to 0. And then if you're finding the actual maximum area, you substitute back into the original. Between these two stages, remember that you do need to test the second derivative to confirm that the value you found is going to give you the maximum or minimum, whatever is required. The same occurs with the volume. So where before we found dA by dx, now we'll be finding dV by dx for the volume. Let's go into an example. Right? Here's a piece of wire 40 centimeters long, cut into two pieces, one forming a circle, the other forming a square. Calculate the minimum area, which can be formed by combining these two shapes, adding the areas together. So there are the shapes, and there's an area. Area is pi squared for the circle. Area equals x squared for the square, where x is the length of the side. So if we're trying to find minimum area, then we're going to find an expression for the area. So there we are. Area equals pi squared plus x squared. Now that has a problem. It has two variables. We need to find it in terms of one variable. So what we're going to use is this 40 centimeters. This 40 centimeters is what the two lengths add up to. So the length here is the perimeter or the circumference, which is 2 pi r, and the length here is the perimeter, which is 4x. So these two must add together to give you the 40. So there we are, 2 pi r plus 4x must equal 40. Remember why we're doing this? We're trying to eliminate either the r or the x from this expression in order to have a single variable. And the only way we can do that is to find one in terms of the other and then substitute. So now I'm going to find what x is equal to. So we move that to that side, divide by 4, it can simplify slightly, and there is what x is equal to in terms of r. So now we can take that and substitute for x in the area formula. There we are. Let's simplify it, and there it is. So there is our formula for the area. Let's just shelve it like that. Now this, we're finding the value of x that will make this a minimum. The value of r, that will make this a minimum. So we're going to differentiate. There we are, there's the derivative. We put it equal to 0. And we're going to solve. We end up with r equaling 2,80. Notice it says 1 decimal place, but I'm going to 2 decimal places. Because if you approximate early, if it says 1 decimal place and you keep doing answers to 1 decimal place, which you're then using after that in the same question, your answer is going to go out and it could be inaccurate. So rather do 2 decimal places throughout and then give your final answer as 1. Either that or store on the calculator in a memory bank if you know how to do that. So now we know the value of r. Now remember, we don't know if that's a maximum or minimum. So therefore, I'm going to find the second derivative. Differentiate that. There it is there. Well, constant, constant. These are positive. So overall, the second derivative is always positive. Therefore, it's a minimum value. Minimum value for r equaling 2,80. Now, the question actually says calculate the minimum area. So there's the area. I don't need to go back to x. I can substitute that in for r. And it simplifies to 56,0 square centimeters. And there's your minimum area that you can form by adding these two shapes together. Let's go into the cat food industry. Here's a company making cat food in enclosed cylindrical tins. It has a set amount of food to go in by volume, and obviously they want to use as little tin as possible. So we find an expression for the area, because it's minimum surface area, so we find area equals. If we're finding a minimum volume, we put volume equals, but this is area. They only have one variable, then we differentiate, and we don't need to find maximum area because it says just calculate the dimensions. So now, how do we find the area of a tin? Because we need the formula for the area of this tin. Well, it's often given to you, but let's go through how to find it in case you're not. It's pretty straightforward. This tin has two circles, one on the top, one below. So that's a pi squared and a pi squared. And then it has what's called the lateral area of the side section. And the best way to picture it is if we take this, we cut off the top and bottom, and then we take tin snips, cut this, and spread it out, we'll get a rectangle. There we are. And the length of the rectangle is the circumference of the circle. The breadth of the rectangle is the height of this tin. There we are. So now, our formula for the area is simply going to be the top, which is pi squared, plus the bottom, which is pi squared, plus the area, the lateral area, which is 2 pi r times h. So 2 pi r into r plus h. That's the formula usually given. Of course, in order to work with it, we're going to multiply it out. But that has a problem at the moment. We need in terms of one variable. And have a look at this. There are two variables. You can't use that at the moment. So we either have to get rid of the h by substitution or the r. So we say, well, what other relationship do we have between h and r in order to be able to do that? Here you are, this volume. 128 pi centimeter cubed. We need to express h in terms of r or r in terms of h. And that's where this volume comes in. There we are. There's the volume, pi squared h, pi squared h. So now I can actually substitute the volume in for there. There we are. And we now have an equation. So either we find h equals or r equals. I'm going to find h equals. It would be madness to find r equals because you're going to end up having to square root. So I'm going to solve for h. There we are, 128 over r squared. The pi's have cancelled. So now I can take that 128 over r squared and put it instead of h in the area formula. And that gives me a formula for the area with just r's. Now we're going to find the derivative. Write this in a differentiable form, in other words, r to the minus 1 on the top. Differentiate and put equal to 0. Solving. There we are. Nice even, nice round number. We get r equal to 4. Now at that stage, remember we need to check that this is a minimum. So I'm going to find second derivative. I differentiate this. We get that. And I say, when I substitute 4 into there, am I going to get a positive or negative? We don't need to know the actual value of the second derivative. We just need to know whether it's positive or negative. Well, that's positive. It's a constant. This one here, the sign of this is determined by the sign of the r, the variable. And the r is positive. So when it's got over r cubed is positive. So overall, that is positive. Therefore, it is going to be a minimum. Now, we haven't been asked for the maximum area, the minimum area. We haven't been asked for the actual area. We've been asked for the dimensions. So therefore, I need to take that r and substitute it into there to find the h. If we're asked the minimum area itself, I'd have put the r into here. but I'm going to put R into there to get the minimum area, the minimum height, so the height for minimum area, and there we are, H equals 8. The practice follows in Optimization 3. The next video, Optimization 3, is some practice for you to try it yourself with solutions.